Today we're going to continue on Venn diagrams and we're looking at something called the addition rule. Now we're also going to look at a couple more bits of terminology. The first words that we're looking at are talking about two events that are mutually exclusive. So if two events are mutually exclusive, then they cannot both occur at the same time. Now an example of this is if I wanted to roll a die and get a prime number, or roll a die and get a 6. Now you can see if I've got a prime number, then I'm not going to have a 6. Or if I've got a 6, it's not going to be a prime number. So these would be mutually exclusive. But if I were to say throw a prime number and get an even number, those are not mutually exclusive, because if I want an even number, then I'm looking at the numbers 2, 4, and 6. Throwing a prime number, one's not a prime number, 2 is, 3 and 5, you can see there is an overlap there of the two. So if there is an overlap of those two events, then they are not mutually exclusive. If there's no overlap altogether, then they are mutually exclusive. When we're looking at a Venn diagram, usually we draw mutually exclusive events as a disjoint sets. So disjoint meaning that they're not connected to each other. So you might have a diagram where you've got your two circles and they're completely separated from each other. Another way we could draw it is to have our two Venn diagrams, our circles overlapping. But what's going to happen there is there's going to be nothing in that overlap section. So when the overlap is empty, then we know that they are mutually exclusive. So if the overlap bit is empty, then what that means is A intersection B is going to have a probability of 0. Or in other words, the size of that set is going to be 0. It's going to be the empty set, not going to have anything in there. If I want the probability of A or B happening in this sort of situation, then if I've got the probability of A and the probability of B, assuming there's nothing in the environment, then that's going to give you every single possible outcome. So if I want to find the probability of getting A or B happening, all I need to do is add together the probability here and the probability there. So the probability of A union B, so A or B, is the probability of A plus the probability of B. And that's only if they are mutually exclusive. Now, if they're not mutually exclusive, then what we can do is we can use our definition of the union. So if I've got A union B, then that's the size of A plus the size of B minus the intersection. And then we can adapt that for a probability question. So when I'm looking at A union B, if I want the probability of getting A or B, I can divide that by the total. So if I divide that by the total, I'm going to divide everything by the total, over total, over total. That effectively gives me these probabilities. So if those are your number of favorable outcomes over the total outcomes. So the probability of getting A or B is the probability of A plus the probability of B minus anything in the overlap. So like what we saw before when we were looking at our Venn diagrams, and we said, okay, we're going to add together all of that and all of that, but we need to recognize that the overlap section has been double counted, so that's why we've taken that off. Using this equation, if we did have mutually exclusive events, we know that the intersection is equal to 0. So if the intersection is equal to 0, you can see that this is going to disappear and we're going to end up with that formula back out again. Let's go do some questions now. So in this one, in a class of 30 students, 15 catch the bus to school, 20 catch a train, and 9 catch a train and bus to school. We're going to find these probabilities that we need. So the first thing that I would do here is I would rewrite this. We have 30 students all together. I'd rewrite these as probabilities. So if we're looking at the 15 who catch a bus, I can write probability of bus, B for bus, is 15 out of 30. We've got 20 who catch a chain, so the probability of catching a chain is 20 out of 30. And then we've got 9 people who catch a train and a bus. So that would be B intersection T. And that's going to give us 9 out of 30. If I want to find the probability they catch a bus or a train, so that means a bus, a train, or both, then what I'm looking for is the probability of B union T. If we go back to that formula, that's the probability of B plus the probability of T minus the probability of the intersection, B intersection T. So because we've already worked out all our fractions, our probabilities, that's 15 over 30 plus 20 over 30 minus 9 out of 30. When we go to work that out, 15, 20, take off the 9, that's 26 out of 30. And then if we simplify that, that's going to give us 13 out of 15. Now that's how we can do it using the probability notation and the formula. You could also do this question using a Venn diagram. So if I were to draw a Venn diagram of this, there's our B, there's our T. We know there's 9 in the middle. Using that 9, we can work out with the bus students, there's 15 of them, so there must be 6 who only catch the bus, because 6 plus 9 is 15. And then with the train, there's 20 altogether who catch train, 9 of them are in the overlap, so there's 11 on the other side. When we add that together, we're going to get 26, so we're going to have 4 on the outside. And so you can see if I want bus or train, there's your 26 out of the 30 students. So you don't have to use the formula, but there are instances where it might be easier to use the formula than not use the formula. The next question, what's the probability that they use neither form of transport to get to school? So what we want is everyone who's not bus or train. So what we're looking for is the complement of bus or train. If I want the complement, that's 1 minus this value. So we can write that as 1 minus the probability of bus or train. So it's 1 minus 13 over 15, which is 2 out of 15. So that's how we can use a complement in order to work out our answer. Another way that we could do this is just using this Venn diagram. If they don't use bus or train, then we're looking at these 4 people on the outside. So if I have 4 people out of 30, that's the same as 2 out of 15. So you can see that that works. Here's a couple more complementary event questions. So a card is drawn at random from a pack. Find the probability that it is not an ace and also not a 2. Now, if we're looking at aces and 2s, you can see that they're mutually exclusive. We're never going to get them both at the same time. A card can't be an ace and a 2 at the same time. So, if I want the probability it's an ace, let's work that one out first. So the probability of an ace, there's 4 of them out of 52 cards. The probability that it's a 2 is also 4 out of 52. So if I want the probability that it's an ace or 2, what I can do is I can just add those probabilities together. So 4 out of 52 plus 4 out of 52, which is 8 out of 52. So I've just left it unsimplified for the time being. It's just a little bit easier to work with if it's fractions, if it's unsimplified, because you can see that all the denominators are the same. At the end, you do need to make sure that you simplify all of your fractions. So we got the probability it's ace or 2, but the question says we don't want the ace and we don't want the 2 either. So we're looking at the complement. Ace or 2, and we want the opposite of that. That's 1 minus the probability it is an ace or 2. That's 1 minus 8 out of 52. If I do 52 minus 8, that's 44. So it's 44 out of 52. And if we simplify that, put it in your calculator, it's 11 out of 13. For part B, find the probability it is an even number, a picture card, or a red card. Now there's quite a lot of things there. So what we need to do is we need to look at each of them separately, or we can look at if we can combine some of them together. Now if we want an even number or a picture card, those are mutually exclusive. You can't have a number and a picture card at the same time. So what we can do is we can combine that together into one. Okay, we're going to work out that probability all together. And then we need to work with the red card. Now, when we're looking at red cards, even numbers can also be red. Picture cards can also be red. Okay, so we'll need to count up those ones very carefully. So I'm going to call this first section, I'm going to call this the set of A. And then the red cards I'm going to call the set of B. Okay, that's going to help us when working out these probabilities. So the probability of A, if we want an even number or a picture card, now even numbers are 2, 4, 6, 8, 10. So there's 5 of them in a suit. And then the picture cards, there's 3 of them, your Jack, Queen, and King. So that's going to be 8 cards altogether per suit. So it's 8 times 4 suits over 52. Okay, so 2, 4, 6, 8, 10. So there's 5 even numbers by 4. And then we're going to add the picture cards. That's going to be a total of 32 out of 52. If we simplify that, that comes out to be 8 over 13. If we want a red card, so probability of set B, there are half of the deck is red cards, so half are black, half are red, so that's 26 out of 52, which is a half. But what we now also need to work out is where is the overlap? So how many even numbers and picture cards are also red? So we're going to work out the probability of A intersection B. So if we're looking at our even numbers, we know there's 5 even numbers and 2 of the suits are red and 2 of the suits are black. So of the even numbers, we're going to have 10 even red cards. So we can have 10. That's your even red cards. With your picture cards, there's 3 different picture cards and again 2 suits of each. So that's going to be 6 red picture cards, and that's over 52. That's 16 over 52. If we simplify that, that comes out to be 4 out of 13. Let me just move this down a bit. So that's 4 out of 13. So if we want it to be an even number or picture card or a red card, we're looking at probability of A union B. When we're looking for this union, probability of A plus the probability of B minus the probability of the intersection. So that's 8 out of 13 plus 1 out of 2 minus 4 out of 13. So when we put that into the calculator, that's 4 out of 13, that comes out to be 21 out of 26. Now there are probably easier ways of counting these, okay? So if we want even number of picture card or red, what you can do is you can count up all of your red cards and then add on any even numbers and picture cards that aren't red in order to get your total, which should have come out to be 42, I believe. Or you could have, like there are other ways that you could approach it as well. But I'm just showing you how the probability notation works, because there are instances where maybe they'll give you these as symbols and then you need to work out your final answer. Or it might be much easier to work it out using these probabilities rather than trying to theorize it or draw Venn diagrams out of it. So here's some questions I'd like you to have a go at. If you've got any problems, let me know.